same proceedings what he's showing.
I think it's this one.
But it can have also this formula.
So not this one.
Not this one.
So it's the Sigmetric paper. The one that you originally had.
Yeah, I'm pretty sure it's this one, right? This tells you how to calculate.
Jefferson, what do you mean? You mean this paper or you mean the paper in proceedings?
The paper in proceedings.
Thomas, go back to proceedings.
That was this one?
Not
No.
this one. The very first paper.
The one that you showed before. Yes.
Yeah, so on this one, scroll up.
Go scroll up.
So equation 2. It's on the second page.
Yes.
So like equation 2. So that's I think. Yeah, so basically it's this game between like you have so X is like the states are of the original MDP, and then Y is the state of nature, which corresponds to the current risk level. And then like first thing to do is to basically solve this game using value iteration. And then afterwards you can reconstruct like what the optimal actions are for player 1, which is basically the decision maker in the original MDP. You reconstruct that using the kind of slope formula, the slope algorithm stuff later.
Oh, so I'm supposed to do something before following?
Yes.
Algorithm? Because I thought this was how you get the value function.
No. It is how by knowing value function you find optimal actions. This is the second algorithm that is needed to implement actual algorithm.
Because I thought the second part of it was where
Yeah, this one. It is the same thing. It is the first one. First thing is to compute VNs. VNs, QNs, this is equivalent.
I'm a little confused because this doesn't require like any input. Like this just you start with the problem and then it gives you the value function. Yeah, I can share it with you.
Look, just a second. First, take n equals 0 and take v0, okay? Exactly. And then implement and find then you complete Vn.
Yeah. So like you don't need to come up with already knowing the value functions because this computes them.
No, this algorithm computes value functions.
Yeah, exactly.
U subroutine 1. You see?
Yeah, that's what this is. This is subroutine.
Exactly, but this is where you compute value functions.
Yeah.
Okay. But how can you compute value functions if you don't have the problem formulation?
You compute them in terms of y.
No, but you need A and B actions. A and B. Where is B?
B is y.
This is the problem formulation. Like these are the costs and MDPs that I came up with. And
B is Y?
these are the actions. So B and C are the actions, and the states are 0 and 1.
As I understand, the actions for the nature is Y. Am I right or no?
Yeah, that's correct.
The actions are Y is the
Oh, the
isn't that the
state.
state? That's the current risk level. And then actions of Y are vectors,
B's.
the B's.
Yeah, that's correct. And then
So you need to tell us what problem you're solving, because we're in dark. What is a written definition, or we need to see the diagram? So basically, we need to understand what problem you're solving.
yeah, these are the state transitions. So you have state 0 and state 1, and this is
So you
saying
have two
like
states, 0 and 1, yeah?
yeah. And if you do
Okay.
action B, this is the probability that you go from 0 to 0 if you do action B.
Just a second. What is the probability? 0, B, 0. What is this?
That's the probability of staying in state 0 if you do action B.
We do. The nature does action B, and you does action A.
Wait, so I think this is the original MDP.
Yeah, this is just a one-player MVP. Yeah.
So you can take this original MDP and then you could, for instance, solve it with a particular starting risk level. So you have the original one-player MVP, and then you consider this like robust version.
No, you need to solve it for all risk levels.
Yeah.
And what this spits out is like value functions for all, like, so the optimal action is different.
I'm sorry, Thomas, move back, please. So what is the original MDP? I don't understand.
This right here.
Because the original MDP doesn't have any B. Original MDP has X, and the rewards are random variables. That's where risks are coming, or transition probabilities are random. So
yeah, so the reward, like, unlike the one that we did in class, I changed it so the reward like is different depending on what state you end up in. So that's where the risk comes from. Because
no. I don't think it is even close to what is right. First of all, you have the original MDP. So you have states, transition probabilities, and rewards. And of course, if everything is deterministic and you play with deterministic policies, there is no issue with the risk. It's a simply deterministic problem. Something is random. Either rewards or transition probabilities or both of them. And that it creates risks. Next step, you find the value functions for all risk levels. And I don't see where, so it's not, you're a student and you're actually a beginning student. You need to learn how to do things. And we're training you. So that's what I'm saying to you. You need to write the formula for
Thomas, am I right that C in the line 91 is the definition of the one-step cost as a dictionary, and in 92 P is the transition kernel for this initial MDP. Am I right?
yeah, that's correct.
And in this initial MDP, as I understand, you have two states, 0, 1, and two actions, B and C, yes?
Mhm.
And for example, if you are in the state 0 and make action B, and the probability to leave this state at the next time is 0.5, and to here you in this case you will obtain reward 1, etc. Yes?
Yeah.
Yeah, so what you do in presentation purposes, you need to draw the graph, the diagram,
Yeah.
for a single problem, and show what you did.
I can
Okay,
definitely.
but fine, but these B and C are confusing because these B and C's are still A's, the actions A.
Better
And
right, left, right, for example, or something like this.
whatever, but not
Yeah.
not B, whatever. So now then the question is whether you calculated the value of functions in terms. Now you need to create a new MDP, which state is x and 0, 1. So 0, 1 multiplied by 0, 1. But in fact, this 0, 1, the second one, the interval, is presented by finite number of points that describe the slopes. And then you find the value function for this MDP by doing value iterations. Where is it done?
Yeah. So the state would be x, y, where x is the original state, so 0 or 1, and then the y is the risk level. And then so this algorithm, this is the main part of the algorithm. So you start out with just by saying, you know, the initial v0 equals 0, or yeah, it doesn't matter what you start with. And then this goes through iterations for each time so I think the algorithm takes advantage of the fact that we know the function is concave, and that allows you to calculate the slopes.
And not only concave, but also piecewise.
And piecewise linear. Yeah. So you can just take all the slopes that you get and sort them, because you know they're going to be decreasing. And there's a similar algorithm.
Okay, for what horizon do you compute V?
I found if you do more than 8, it starts to be pretty slow. So yeah, maybe the efficiency could be improved.
Okay, you made for 8 steps. Yeah. Okay. Okay, and then you implemented the algorithm, yeah?
Yeah, I haven't done like the second part of this, which I haven't done step 3 yet, but I finished where you get the optimal actions. So I know there's a lot here in setup, but it's giving you optimal actions where there's more than one optimal action depending on the risk level. So in some of these, like the optimal action sets might be more than one.
Okay, can you show our algorithm, the second one, which actually chooses, maybe in the paper, for example, because it says what is the initial data.
In this paper?
Yeah, algorithm in this paper.
They write out the algorithm like specifically. Right here. Yeah.
So
you start out with these.
Slightly more. You have inputs.
Yeah.
We need to have here inputs like Q function. We discussed.
V function is enough.
V function is enough, but we discussed we need something else here, as I remember. Or no?
No, they simply have the particular form which is described in the ACM paper.
Okay.
Yeah, V and Q, they can be used interchangeably. Because if you have a V, you can compute Q, if you have a Q, you can compute
We
V.
understand this.
Okay. And so this is so basically what you do, you run various iterations and you do it 8 times. And after each iteration, you save functions Vn in the form described in the ACM paper. In ACM paper, you use graphical implementation. And the next step is to run the algorithm.
Yeah, I haven't done this part yet. I have all these like A-star success.
Very good. So, do you have a paper by Patrick?
Patrick.
Could you move it down? I don't remember where they cited in this version.
There is a property, there is a useful property for subdifferential of, no, or in our case, not subdifferential, for superdifferential, superdifferential of maxima of some functions. This is a convex hull of derivatives or of tangencies of each line.
I'm sure that it's mentioned there in this paper. I'm sure.
And we can use this in this algorithm, I see.
I think it is used, yeah. It
So
is used.
is that for calculating like the minimum of the convex functions, like we were talking about last time?
We talk now about the next step, how to calculate, after that, how to calculate its super differential.
Okay, for the derivative. Okay.
As a convex hull of that tangencies for that linear functions or affine functions.
Okay.
I'm not sure that this is needed for the algorithm, but this theorem is written somewhere.
Yeah, I think that will be.
This is property 5.1. Yeah.
Of course, each time you can take, for example, a subdifferential of some of the lines, but in the general,
You probably in 5.1 that if class is minimum and if is maximum.
you can take the minima and take the subdifferential for that minima, but you can use another formula. It depends on what method gives, what method is more quick.
Yeah, but this formula basically says that the differential of value function, the slope of a value function, is equal to minimum slope of future functions. And this is exactly, I believe, the result that you mentioned.
Oh, yes, you can use this property for directional derivatives, for example.
Yeah. We actually just
I'm not sure whether we need to calculate the minima. I mean this. I think that in some cases you do not need to calculate minima.
No. Let me explain to you. This is done to compute right slope and left slope.
I
The
understand.
right slope it is minimum. For left slope it is maximum.
But if you need sum of the number between them, you can take, for example, tangents of one of them. Not especially. No, you can choose it randomly.
No. This is done for vertices. vertex is defined by two slopes, right and left. And for the right slope, it is surface plus, and for the left slope, it's minus. Because it depends on what you're talking about. If you're talking about
I see. For right slope is minima, for left maxima. I change them. You cannot take an arbitrary. You need to take. I see.
Yeah,
You need to compute them all.
actually, when they do order, it allows us to find these coefficients.
I think on the possibility to do not compute minima, but I do not see the algorithm. You need to compute at least one of them.
Maybe there are, but I'm not sure that they will work, because this minima will be in fact maxima of the previous vertex.
No, yes, this is a good idea.
You're right, but maybe in some cases it's efficient to do it.
No, you can. I see. You can do
It's
this.
linear maximum. So it will be this minimum for this point will be maximum
For the next.
the left one. But again,
He can do this, for example, not for 8, for 16
yeah.
with the same speed.
Yeah. If we move from one point to another, we can just take this
For odd and
minus,
even, the same.
Yeah, but this taken not with respect to next vertices in each line, but with respect to maximum of them. So the last one.
Да.
Yeah, so it's possible, but actually we may not have them calculated. So basically, it's already a permutations issue. I don't know whether Thomas follows us.
I think he calculated it directly.
Okay, so Thomas, so then first of all, write verbal description of the problem. Write the MDP diagram that we understand what we're talking, and then write that this is V0, V1, and so on, V8. Yeah? And V8 may have many slopes because the number of these points increases.
Yeah, it does.
And then we'll start from there.
Yeah, these are all the slopes.
Can we compute this more efficiently?
Yeah, this will be the next question.
Yeah, it's definitely. So I think Python might not be the best if we're going for efficiency, because I'm using.
I suspect that for large N, we should take some neural network approximation.
Eugene, I mean what I mean. In neural networks, for example, you the next iteration, as usual, is grounded on the previous one. But here, so I do not. No, I think that we can either modify or it's already done. That at the next iteration you want that we do not recalculate the previous. For example, the aim to add, to calculate at most one more point or something like this, not all.
Yeah. Because the function becomes more and more complicated every time.
But do not recalculate previous points.
No, don't need to recalculate because already calculated.
Yeah, it's not the issue that you need to recalculate, it's just that the function is becoming more and more like fine, and there's more and more slopes. But if we sacrifice some of the breakpoints and just hold an approximate version of the function, then the algorithm would run much faster.
Yeah, but it's early for us to talk about it. Let's look how the solutions look, exact solutions for small numbers, and then talk how to do it for.
I see that we need here to make some efficient approximations because at the horizon 8 we have a lot of points. We need to approximate this, but something that
Yes.
Maybe just placing a limit on the number of breakpoints. Like only store.
I think we need to modify the algorithm. But first of all, we need to implement it. But
Exactly what I'm saying. Let's implement what we have, look at more carefully, recalculate what Rui was doing. So let's still be in the learning mode, and then we'll think how to improve it. Okay? Anything else? Unfortunately, I still didn't work on the paper, but I'm just one step ahead from doing this. Probably already tomorrow we'll be working on it.
Eugene, do the Thomas can share this for all of us, or it's early, or it's too early? For example,
No, he can, of course. My understanding that he needs to put it somewhere, send us the access.
no, for example, we can think about the next steps and of course
He didn't finish coding the algorithm. My understanding that he coded only
the first
the classical part,
yes,
the value
yes.
iterations.
But he have a very good improvements and
Compared to what was a week ago, yeah.
Yes, I can share this with everyone. Yeah, I like to work on it in Jupyter Notebook so I can.
Yeah, but you have no problem on the copy.
Yeah, I'll work on it on here and then I'll keep updating it. So you guys can see.
the recent version, for example, we can make this date, for example, today or something like this. And when you will improve something, you may no, we can not use versions. You can make another file with another date. It would be more useful for us, I think.
Okay, yeah, so I'll share this with everyone. And then
If is some ideas on parallelization for it, for example, or something like this, because
Paulo, it's too early. And in general, dynamic programming problems are not for
no, we understand. We wrote, we read your papers with Jefferson on this, but we can.
Of course, we can use different.
I think we can make some mathematical trick that can give us such opportunity, or for example, break the curse of dimensionality or something like this, because I see this is a very difficult on one hand, but very important problem.
There are some more basic things for realization. For example, if we make programs for projects,
Okay.
let's first of all
We can
come to
discuss it
another
later.
because now, of course, there are different ways to go.
Uh-huh.
Okay, then do we meet in a week?
Okay.
Yeah, I think this time works for me for next week.
Yeah, if I can move it to 12, then will it okay?
Mm-hmm.
Yeah, that.
Because just I have a meeting that starts at 12 for 4 or 5 hours. We're interviewing some people for department position, department chair, different department, I don't remember. Okay, very good.
So for next week, so we're meeting at 12 your time next week.
Let me look at my schedule.
I'm not sure if 12 will work for me. So, if we could do it like a little bit earlier, that would be good.
Just a second. So I'm looking at 17th. Yes, it's booked from 12:30. Yeah, let's meet at 10. If it's good for everybody, let's meet at 10. At 11, I'm sorry. At 11.
Okay, I'll send out the invite with the correct Zoom link.
Yeah, okay. Thank you. Thank you very much.
Okay, so we'll talk next week.
Yep.
Good.
Okay.
All right, see you then.
Bye-bye. See you.
Bye.